Welcome to Lesson 15, Equations of Graphs of Proportional Relationships Involving Fractions. This is the last lesson in Topic C. Topic D will begin after this, starting with Lesson 16, and it will go on to ratios of scale drawings. Okay, this right here is our last lesson in Topic C. Before we do get into this lesson, I want to review a few things with you. Way back when, lesson 10 or so, we talked about a few things, and those few things I want to discuss right now are our unit rate, okay, unit rate, ordered pairs. And again, there are many of you who know what all of these mean, but bear with me. And the meaning of a few points, one is that point 0, 0, and one is the point 1, R. Okay? All right, where x equals 1, and then R is the rate or the the y value. Okay, so let's talk about a few things first. So this idea of ordered pairs. When we mention ordered pairs, we are talking about x and y on a graph. Okay, here's our x-axis. Here's our y-axis. These all here that I have written here are all ordered pairs. Okay, so an ordered pair would be, for example, 2, 4. Now 2, 4 means where x is 2 and y is 4. Okay, and you can see that right here. Here's x as 2. Here's y as 4. Okay, 2, 4. Right? 4, 8 is the same way. This is going to be x as 4 and y as 8. 6, 12 is the same. 6 and 12. And we can look and we can see one of these ordered pairs that does exist on this line is actually this one. So let's go ahead and talk about that point 0, 0. And the point 0, 0 is our origin, and you can see it right here. And the fact that this straight line passes through the origin, okay, will give you the right to say that this is a proportional relationship. Okay, so we have the clearance to say that this graph represents a proportional relationship because it has the, or gosh, I'm trying to think of it. There's a word I'm missing here, but anyway, it does pass through the origin, and it does move in a straight line with a very, very particular slope, which we'll talk about sometime later. Okay, now the significance of this point right here, this 0, 0, the 0, 0 is when x is 0 and y is 0. That could be, like we've seen in the past, sales of an online website and money earned by the singer who produced the song. Okay, so 0 online sales, 0 money to the singer. Okay, for example. So the significance of this 0, 0 is that it does give us a hint that this graph is does indeed display a proportional relationship, but also it's a place where both x and y are 0. Okay, all right. Now the other significant point I wanted to just to remind you of is this point here, and that is 1, R. Okay, and that is the place where x equals 1. Okay, again, you can see every time we write an ordered pair, we write it in the form of x, y. Okay, so where x equals 1, in this case, y equals 2. You can see that right there on our on our graph right there. Now what's very special about this point right here, which is actually this point, where x equals 1, is that that represents our unit rate. Okay, that's our unit rate. All right, and our unit rate is found down here. And remember we talked about that unit rate being k. K equals y over x. So remember, and I've said this so many times, and just wonder if anybody could actually repeat this to me if I asked. But yes, we are looking at y as a, anybody want to fill in the next word for me? As a function of x. Y as a function of x. Okay, because remember, x is our dependent, is our independent variable. It changes, okay? And y, of course, was our dependent variable because it depends on x, okay? So y as a function of x, every time x changes, y will change as well, okay? So y as a function of x. And if we just made a fraction out of it, I just took one of the points I had originally plotted, which was this one right here, and that was 4 over 2 because it's y over x, and that equals 2. So our unit rate on this graph, this proportional relationship, is 2. Okay, 2. So for every move of x, there is a move of 2 on the y-axis. Okay, and you can see that. See how they compare. 2 compares to 4 that way because 4 is 2 times 2. 8 is 4 times 2. And 12 is 6 times 2. Okay? So again, we have these things to remember or to recall. Again, I know this is all a little bit of review, but it never hurts. So we have unit rate, y as a function of x, ordered pairs, which are all of these here, these various points on the line. We have the significance of 0, 0, which is actually the origin. It's where x equals 0, y equals 0. The significance of 1, r, where 1 is the value of x and r is the actual unit rate. And then we have, that's what we have. Okay, so there's a little review. So with that review, I'll let you know that what I want you to be able to see here, the goal, is to help you see the relationship between the unit rate and the changes in x and y. Okay, and hopefully you're getting that idea, and you might have known it already. So let's go ahead and go back. Let's start here with our first example, mother's 10K race. Now, K, many of you might understand, and some of you are racers out there and are runners. The K stands for kilometers. Okay, kilometers. A 10K race is 10 kilometers. And a kilometer, again, as many of you will know, is 1,000 meters. Okay, it's 1,000 meters. So you see a meter stick in front of you, think of 1,000 of those, and that's 1 kilometer. If you're going to do a 10-kilometer race, that's going to be 10,000 of those. Okay, which sounds like a lot. Sounds pretty impressive, huh? But 10 kilometers is about approximately, and a lot of us again that do race, do 10K races and such, it's about 6.2 miles. That's the conversion. Okay, about 6.2 miles. Very popular race is a 10K race. Okay, 10K, 5K is another, and that's about 3.1 miles, as you can imagine. Okay, half of this one, half of the 10K. Okay. Okay, let's go ahead and read that. Now that you know that, 10K race, real popular race, 10 kilometers, and it's about 6.2 miles. Okay, I'm going to go ahead and read this to you. Sam's mother has entered a 10K race. Sam and his family want to show their support of their mother, but they need to figure out where they should go along the race course. They also need to determine how long it will take her to run the race. Here we go. Oh, geez, don't want to do that. Determine. They also need to determine how long it will take her to run the race so that they will know when to meet her at the finish line. Okay? So now, previously, his mother ran a 5K race with a time of 1.5 hours, which is a very long time. I'm not sure she was even running. Anyway, that's besides the point. So let's go ahead and assume, again, we're going to assume Sam's mother ran at the same rate as the previous race in order to complete the chart. Okay, so we're making an assumption. Okay, we are assuming. And again, this is all we can do. We can predict sometimes. You know, we can predict based on someone's prior rate, running rate or unit rate, and that's what we're going to try to find out right now. Is mom's unit rate. So here, our task right now is to create a chart that will show how far Sam's mother has run after each half hour from the start of the race, and then graph it on the grid at the right. Okay, so what I want you to do, I want to give you an opportunity to do this yourself. Pause the video now, or pause the presentation now, and go ahead and try this, and then come on back and we can do it together. Okay, so hopefully you figured out that step one was that you needed to find Sam's mother's average rate for her previous 5K race, because remember, we are assuming she's going to run at the same rate, so we can predict when she'll be at the finish line, or where she'll be at any given hour, or I guess half hour during the race. So for that, we just needed these two bits of information. We needed 5 kilometers. That was the race. It was a 5K race, and she did it in 1.5 hours. Okay. Now we're trying to find a per kilometer, or per hour rate. Okay, so we're trying to find a kilometer per hour rate. Okay, so in that case, we are going to need to have, we're trying to find 5K as a function of the 1.5 hours. Now I've turned that into 3/2 hours for our division purposes. Okay, so if you remember now, we're going to just use the numbers that we have in front of us. So if we're going to go ahead and divide 5, and this is 5 kilometers, I don't need the K right there right now. We're going to divide that by 3/2 hours, which is the same as 1.5 hours. Okay, remember what I do with that now. Again, I'm going to divide 5 by this, so I want to do 5/1 divided by 3/2, which, again, I'm going to say this again and again, keep doing this, is the same as, or what you need to do is 5/1 times, remember, the reciprocal. Okay, so then if you did that, you would get 10/3. Okay, so 10/3 hours per kilometer. Okay, and another way to look at that, if we turn that into a mixed number, we would have 3 1/3 hours. Okay, 3 1/3 hours. So we're going to go ahead and apply this rate, 3 1/3 hours per kilometer. Okay, per K. So here we go, right here. 3 1/3. So for every kilometer she ran, it took her 3 1/3 hours. Now no, sorry, hold on a second. I did that wrong. Excuse me, because that looked really weird. Okay, no, because I did this right. I did all this correctly. Yippee-dippee. But this is actually 3.13 kilometers per hour, because of course, as I said before, I was trying to find a per hour rate. That's why I use that as my X value. Okay, so yes, 3 1/3 kilometers per hour. So every hour she ran that distance, 3 1/3 kilometers, which is still very slow. Okay, so excuse me. Let's go over here then, and let's fill in this chart. And again, hopefully you did that already. Now, it might be handy if you you had both of these unit rates at your disposal, okay? Because they are exactly the same, okay? 3 1/3 kilometers per hour is the same as 10/3 or 10/3 kilometers per hour, okay? They're both equal to the same thing. They are equivalent. Their difference in the way they're written will help us in our calculations over here. So, for example, the unit rate of this one here of 3 1/3 kilometers per hour is easy for me to plug that into the 1 hour slot. I could easily plug it into the 2 hour slot just by multiplying by 2, and that would be 6 2/3. Okay, and then add another 3 1/3 to 6 2/3, because I'm going to fill out this 3, I get 10. Okay, so 10 kilometers. Now with the 1/2, I mean, not as easy to do, but if I use my 10/3, I could easily do, and again, half of an hour implies multiplication, so I would do 1/2 times 1/2 of 10/3, 3, and that's going to equal 10/6, which is going to equal, what is that going to be? It's going to be 1 4/6, which is the same as 1 2/3. Okay, 1 2/3. Alrighty, and we could have actually, if we had done our cross cancellation here, we could have actually done this, just canceled these out, which would have made that a lot easier, and that would have been 5/3. Actually, so much easier to do this cross canceling right away. 5/3, which is more easily seen as 1 2/3. Yeah, please do that. Much easier to do. Okay, so 1 2/3. So this is 1 2/3 kilometers in a half an hour. And then I'm just going to go ahead and fill in the others here. So what do we have here? We have 1 1/2 is going to be 5. Okay, so 5, and you can see that every half an hour is 1 2/3. So we could just keep adding that on right here, and then right here we would have 8 1/3. 8 1/3 kilometers. Okay, so now we have an idea of where Mom should be at all these given points for every half hour. We're trying to find out where she's going to be on course. Okay, so the next thing to do is go ahead and plug in or plot all of these points. Okay, so I'm going to go ahead and pause and do that. Now, this may not always be the case that you'd be so fortunate, but it's nice to actually, for me, I like plotting the nice neat points first, where we have, and it's really nice that on the x-axis here they have given us a half-hour increments. You know, you can do that yourself when you are creating a graph, and it's always nice to create your graph and to we say to grade your graph or to graduate your graph in a way that suits your purposes. Again, and a lot of times that's done by companies and corporations to make themselves look a little better than they actually are. But in this case, I plotted the 1.5 and the 5, where 1.5 comma 5, which is right here, then 3 comma 10, which is right here, which is nice and clean. Now all the rest of these points where we had 1 and 1, 3 and 1/3, you know, I mean that's right there. Then we had 2 and 6 and 2/3. That's about right there. There. Okay, they're right about there. It's not right quite on the line. And then we had 2.5 and 8 and 1/3, which is about right around there. Okay, and you can see they all fall on the line. Okay, and so what are some of the specific things you can say about this graph? Forms a straight line, and it runs through the origin, right? So it relates hours to kilometers run, and then the straight line through the origin means that the values are proportional. Okay, so it's a proportional. It shows a proportional relationship. Okay, because it fits those criteria. Okay, proportional relationship. And okay, so what is the connection between the table and the graph? Okay, so the time in hours is on the horizontal axis, and the kilometers run is on the vertical axis. And so the coordinates of the points on the line are the same as the pairs of numbers in the table. Okay, so that's always going to be the case. Of course, we don't have the origin written in the table. We don't usually, but there will be a time later on in your algebra life that we will, and not too far in the future, where we will need to plug in 0 for x and or y for very, very important reasons. But anyway, in this case, we have taken these come right off of the table, right out of the table. There they are. 1.5, comma 5 is right here. Okay, 3, comma 10 is right here. And then all the rest are there as well. I haven't actually labeled those on the graph. Maybe you have. Hopefully you have. Okay. Now they asked you another question here. Was question C, which we can barely see on your screen here, but you can see it in front of you. It says, what does the point 2, comma 6 2/3 represent? And at that point, after 2 hours, she has run 6 2/3 kilometers. And again, you can see that right here. Here's 2 hours, go up to there, and right there at this point, she has run, that's right about there, 6 2/3 kilometers. Again, much easier, of course, to see on your table over here than to see on a graph. Yeah, okay. Okay, so if we want to write an equation that models the data in the chart, this, of course, is a distance and time chart. Okay, we had, so go back here. We have distance on the over here. We have distance on the side here as the y-axis, and we have time down here. So d and t. Very, 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 very famous equation right here. D equals r times t. You're going to see that quite a bit in physical science when you get to 8th grade. Okay, and some of you who are in 8th grade already, well, hopefully, or we'll see that pretty soon, or have seen it already. Anyway, so when we figure out our unit rate, remember our k, or our unit rate, equals y as a function of x. So in our case, it was distance as a function of time. Okay, that's what it was. We came up with 10/3 kilometers, okay, per hour. Okay, that's how we write that, 10/3 kilometer per hour. All right, now we have a rate. So this is our r over here as well. Okay, here is our r. Okay, so we could say that d, distance, equals 10/3 t. Okay, d equals 10/3 t. That could be an equation. All right, if we're going to use d, r, and t, or we could say d equals 10/3 h for hours, okay? Because if we go back and we see, for every, so d, the distance here, this would be our d, in that case, d, for every d, we would multiply that by 10/3 times the number of hours, okay? So each time we go a d, so for example, if we went 3 1/3 kilometers, we were going to multiply 10/3, or 3 1/3 times 1 to get our kilometers run. Okay, so 10 D equals 10 over 3 H hours, or D equals 10 over 3 T, which in this case is our time. Okay, so in this next example, it's going to be a little bit different. You're going to actually be given, or you are given, a graphical representation of this relationship between weight in pounds and cost, and then you're going to be asked to use that graph and to answer some questions. Use the graph and the table. So let me go ahead and read this to you. If I sound like I am talking quickly, I might be talking a little extra quickly because I am running out of battery on my iPad here. So, after taking a cooking class, you decide to try out your new cooking skills by preparing a meal for your family. You have chosen a recipe that uses an organic mushroom mix as the main ingredient. Using the graph below, complete the table of values and answer the following questions. Okay, I guess there are a couple of holes in there, aren't there, that we need to actually fill in. So let's go ahead and do that. Okay, so why don't you go ahead and do that? Go ahead and fill in these couple of blanks, and of course you need to figure out a unit rate. Okay, and again, if you look at this one, you may be able to figure that out. If you have, for every half pound costs $4, pound is going to cost, of course, 8. Okay, I guess we're doing this together. Okay, and then if we have, then of course, it's going to be 2. Okay, so again, we filled in these couple of voids there. All right, and we can see a unit rate. So let's go ahead and let's go down. Let's get these questions here. Okay. All right, so is this relationship proportional? How do you know from examining the graph? And of course you know it is indeed yes, it is proportional. And as you can see, we have a graph that goes through the origin and it is in a consistent straight line. Okay? What is the unit rate? Cost per pound. Okay, and we can see if we go back to our, this is our unit rate, because our unit is per pound, unit rate. Okay, so per every pound, so where this weight here, this X value is 1, remember, that is going to be our unit rate, so our unit rate therefore is $8 per pound. Okay. Write an equation to model this data. Okay, we could do something like cost equals 8 weight. Okay, so C equals 8 times W, or we could do X equals 8Y. Okay, and again, if we look over here, all right, X equals, Y equals Y equals 8x. We have y equals 8x right here, because every time we have y, we have 8 times that x. Okay, or C, as in the cost, would be in W. Okay. All right. So again, C equals 8W, or y equals 8x. Okay, so what ordered pair, or which ordered pair represents the unit rate? And remember, the unit pair that represents the unit rate is where x equals 1. Okay, and if we go back and we look where x equals 1, that is right here, and then y equals 8. So if we were to make a unit pair, unit pair out of that, our unit pair would be, or ordered pair would be 1, 8. Okay, and if we looked at our graph, here is here's 1, and then here is 8 right here. This would be our unit rate is right there where x equals 1. Okay? Do that again. What does the ordered pair 216 mean in context of this problem? And again, we can see, we just look at the table, 2 and 16, that's right here. So where you bought 2 pounds of mushrooms, it cost you $16. That's what it means in context of this problem. And again, they're always trying to get you back to the problem, to know these just aren't simply just numbers to put in parentheses with a comma between them, but they actually mean something. Okay, so 2 pounds of mushrooms, let's say called mush, costs you $16. Okay, this means something. So if you could spend $10 on mushrooms, how many pounds could you buy? So if each pound is going to cost you $8, all you're doing is multiplying by 8, okay, for every pound. If you buy, oh, sorry, I'm doing this wrong. Sorry, incorrectly. Okay, so we have $10 on mushrooms. How many pounds could you buy? Okay, so if we're going to go ahead and use that, C equals 8W formula, okay, we would say that we have, again, we can look at this a little bit differently now because, well, let's go back and look at some of our numbers. Okay, so if we just use our C equals 8W equation, we can figure this out. But now we need to plug this $10 into where it belongs. So it belongs over here in the C part, okay? The C or the Y. So 10 equals 8W. And again, just like we've done in the past, you want to isolate the W over here because that is our variable. That's our unknown. Okay, so we're going to isolate this. And the way we isolate it is by dividing by 8. Remember, we divide by 8 because that's where we're going to get, because 8 times 8 is going to equal 1, and that's going to leave a W there by itself. So, and again, putting this W on the left side would have been a little bit easier. But so 10 over 8. Okay, so 10 over $8, or yeah, 10 over $8. Okay, well, not 10 over $8, but 10 over 8 equals W. So 10 over 8 pounds. So that would be 1 2/8 pounds, or 1 1/4 pound. Okay, another way to abbreviate pound is with that pound sign. Okay, so 10 over 8 equals W. So W therefore is going to equal 1 1/4 pounds, which is the same as 10 over 8 pounds. Okay, so 1 1/4 pounds can be purchased with $10. Okay. And the last question, a little bit easier to figure out, is that, so what would the cost of 30 pounds be? 30 pounds of mushrooms, and again we have C equals 8W. Again, always applying applying the equation that we came up with. So C equals 8W, so C equals 8, and then we'll just plug in our W, which we know is 30 right here from here. Okay, and so C equals 240. Okay, so $240 for 30 pounds of mushrooms. Okay, so yeah, in summary here, well, before we get into this little summary that's written here, I just wanted to just to talk to you about the usefulness of equations, okay, as models, because they can help us determine very large or very small values that are difficult or impossible to see on a graph. So when you have a graphical representation of something, it's easy at times to see what you can see. But when you're working with very, very large numbers, or numbers that are either outside the realm of that graph, or numbers that are in between 2 points that are very, very difficult to see, using an equation is extremely useful, as we saw before with the cost of the mushrooms. Okay, I am down to 11% battery, so I am going to start talking a little bit faster even. No, probably not, but I think I can get this done. Okay, so our lesson summary here is proportional relationships can be represented through the use of graphs, tables, equations, diagrams, and verbal descriptions. Okay, so we can see them through all of these things. In a proportional relationship arising from ratios and rates involving fractions, the graph gives a visual display of all values of the proportional relationship, especially the quantities that fall between integer values. And what that is, between integer values, whole numbers, integer values. But again, not as useful as as having an equation at your ready. Okay. I noticed in the problem set to come up, constant of proportionality comes up again, and just to know that constant of proportionality is is pretty much the same as your unit rate. Okay, constant proportionality. Having some more trouble with my pen. I'm going to get this fixed eventually. Okay, proportionality. You may see that. Don't be confused. Again, I said it several times, but it's just that unit rate that creates that proportional relationship throughout a series of values within a problem, on a graph, etc. Okay. So yeah, this was a quick lesson. Any questions? Please get back to me. Good luck on your problem sets and the exit ticket. Okay. See ya.